All right, this is lecture 14, part 1, in which we talk about brittle fault rocks. And in part 2 of lecture 14, we'll talk about fault classification. Okay, so during frictional movement along a fault or within a fault zone, rock may be transformed into a variety of what we call brittle fault rocks, most notably breccias. And so you know from your GO 101 understanding of different types of rocks, a breccia is a rock with angular clasts in it. So brittle fault zones, they're pervasively fractured and crushed with motion on faults or on fault zones. And so we use the term comminution to describe the action of the rocks being broken down into progressively finer and finer size fractions during faulting. So the specific nature of fault rocks, it will end up depending, as we'll see, will depend on the starting materials, so the rock type or the mineral type, the conditions, which are the pressures and temperatures, and the deformation mechanisms. In other words, whether things get fractured or they deform by frictional slip or mechanical twinning, or the various creep mechanisms. So the focus of the rocks that we're going to talk about today are going to be fault rocks that are formed under conditions that cause the rocks to be damaged in a brittle fashion. So in this realm up here. Okay. Later in the semester, we'll cover fault rocks that are formed at deeper conditions down here and formed during ductile deformation when we talk about shear zones. Okay, so let me switch over to DocCam. Let's define a couple of words here. Okay, so we can classify our brittle fault rocks into two kind of series, the Breccia series and the Cataclasite series. Okay, so let's write that down. Two classes of brittle fault rocks. The Breccia series and the Cataclasite or the Cataclasite series. And we'll look at the differences between these two in detail. Okay, let's look at the Breccia series first and kind of define some important characteristics about the Breccia series. Okay, so in the Breccia series, our Breccia series fault rocks are characteristically incohesive. And this word incohesive simply means that it can be made to fall apart in your hands. In other words, they're not well indurated. Okay, they're easy to crumble if you squeeze them at all or whatnot. Okay, and then so let's define this in more detail. Our brittle Breccia series rocks are brittle fault rocks that are marked by angular clasts in a finer matrix. Okay, brittle fault rocks marked by angular clasts in a finer matrix, and generally about 30% of the fault rock is matrix, and so the rock is clast supported. And there's generally no preferred orientation in our clasts. Meaning that there's not really a fabric to the class, like a metamorphic fabric. Although, let me just qualify that with the classes often appear they often appear rotated and have a jigsaw kind of jigsaw appearance, where you can see kind of where and how the class fit back together. If the grain size is large enough, I should say also. And even though there's no preferred orientation in our class, and we'll look at this in detail a little bit more, the fault zone often has an architecture to it. Okay, so although I said these Breccia series rocks are incohesive, they can often have a little bit of cohesiveness if they've been silicified or mineralized by fluid flow through the pore space, basically. Okay, so we're gonna have four main varieties of our Breccia series rocks. And we're gonna base it on class size. So our names of our Breccia series rocks are mega Breccias, in which the class size are anything greater than 0.5 meters. Okay, so pretty large. And then just simple Breccias, in which our class sizes they're larger than 1 millimeter and smaller than 0.5 meters. And then micro Breccia, our class are larger than larger than 1 millimeter and smaller than, they're larger than 0.1 millimeter and smaller than 1 millimeter. And then our smallest size is gouge, in which the class sizes are smaller than 0.1 millimeter. In essence, clay-sized particles. Okay, so that was Breccia series. And we also have Cataclasite series. Okay, so cataclasites are, for one thing, they differ from our Breccia series in that they're cohesive. They're cohesive and well indurated. Such that they're often more resistant to weathering than the surrounding parent rock around them that are unfaulted. And when rocks erode around them, they're kind of left behind as this resistant rib of rock. Okay, so they are still brittle fault rocks. That are marked by angular clasts in greater than 50% matrix. And here's one important way that they differ from our from our Breccias series rocks is how much more matrix there is. So 50% matrix or more, and so often these types of fault rocks are matrix supported, not class supported. And they generally have no preferred orientation of class. And the classes are isolated in this matrix, so they don't have that jigsaw appearance to them where it's easy to see what pieces they might fit back together with, depending on the class size. Okay, so we have two categories of cataclasite series rocks, and again, based on the sizes of the rock, or the sizes of the class. We have just simple cataclasite, in which our class are greater than 0.1 millimeter and smaller than 0.05 millimeter, or sorry, 10 millimeters. And ultracataclasites are smaller. Their class sizes are anything smaller than 0.1 millimeter. Okay, so a unique thing too that sets cataclasites apart from the Breccia series is that they're cataclasites and ultracataclasites is that they have this fractal character to them, meaning they're self-similar at all scales. This fractured angular appearance to the grains with an appearance of 50% or more matrix is the same at all scales, from outcrop to hand sample to thin section to SEM image. Okay, so and ultracataclasites are or have a fractal character. Meaning they're self-similar at all scales. Okay, so that's our cataclasites. I'm gonna look at some pictures here in a second. And then we have kind of this oddball Breccia series of rock. It's called a pseudotachylites. So this word tachylite, it's kind of an old school term for a glassy basalt. And these aren't glassy basalts, but they're basically they're melted fault rock. Okay, so they're unlike breccias and cataclasites. And they are unlike breccias and cataclasites in that they're created by the frictional melting of, but not the grinding and fracturing of fault rock, which our Breccia series and rocks and cataclasite rocks are made from. Okay, so created by the frictional melting of, but not grinding and fracturing. And they have this glassy this glassy to cryptocrystalline. Texture, meaning they melted and cooled really rapidly, and that they don't have a crystal form. They're literally a glass. So they're generally brown to gray to black. And sometimes they may have tiny crystals, less than 1 micron. In an isotropic glassy ground mass. Okay, and they occur in vein-like arrays, some of which have this spider web-like appearance. Okay, so we can nicely summarize the environment in which these different fault rocks form on this conceptual cross-sectional diagram that should be on your screen. Okay, so there's 2 basic regimes of fault rock production: an upper in this sector here, an upper frictional regime where frictional strength increases linearly with depth because of the increasing confining pressure. And hence we get incohesive breccias in this upper part and gouges in the upper 1 to 4 kilometers of the crust, okay, or incohesive gouge and breccia. And at deeper depths, we get the formation of cohesive, well-indurated cataclasites from depths of 4 kilometers down to 10 to 15 kilometers, depending on the local conditions. And this notation EF, that's elastic frictional regime. QP is quasi-plastic regime. And then frictional behavior progressively gives way to the plastic regime across a depth transition between where temperatures increase from 250 to 350 degrees. And so at these depths, the power flow laws start to dictate rock strength. We're crossing basically the brittle ductile transition at these temperatures and depths. And the 3 creeps are the mechanisms of microstructural deformation at these depths. So at these depths, the fault rocks that form down here, those are called myelinites, which we'll talk about in later chapters when we talk about shear zones. Okay, so from this diagram, though, you can see that pseudotachylites, they span a range of depths in our brittle or our frictional upper regime. And so this type of rock can form if the conditions are basically just right. So the formation of pseudotachylites, it requires a couple things. It requires a powerful shock under high pressure conditions and the instantaneously imposed strain. In other words, an earthquake event. So we can think of pseudotachylites basically as a fossilized earthquake event, though not all earthquakes generate a pseudotachlite. Okay, so let's look in more detail at breccia rocks. Ooh. Okay, so again, breccias, they're unsorted, angular class. You can see these nice angular class in here of wall rock set in a finer grained matrix of crushed wall rock. and the matrix compose 30% or less of the breccia, and is subordinate to the angular class. Okay, so we can see in this picture, even though there is a lot of matrix, there's much less matrix, less than 30%, relative to our angular class. And even though from this picture it doesn't necessarily look like it, these are class supported by and large. Okay, so dilution, or dilation I should say, and volume increase are characteristic of brecciation, or the brecciation class of fault rocks, which implies that the formation of breccias is favored in environments of low confining pressure, and or high fluid pressure, and generally low temperatures. So in other words, typically at depths of 0 to 4 kilometers. And voids that form during the pull apart and dilation at the time of faulting, those result in a typically incohesive and poorly indurated rock. So that's why our breccia series of fault rocks are not well indurated and not cohesive because of that dilational nature and the low confining stresses that they're under. However, the void space can often get filled later by precipitation of minerals from the circulating of groundwater or hydrothermal fluids. And from this standpoint, fault breccias are actually pretty important from a mining geology perspective, or from a geothermal geology perspective. They're the conduits oftentimes that hot fluids are moving up on, at least in the basin range where I'm familiar with geothermal systems. Okay, so something called fault gouge, right, which we talked about, is the finest grain feature in our breccia series of fault rocks, can actually be a pretty important fault rock that develops in the course of fault brecciation. So gouge, again, is brecciation with very small grain size, basically clay size grain size, so less than 0.1 millimeter in size, and it's from the ultra grinding, often in the heart of the fault zone. So the distribution of breccia series fault rock within a fault zone, it varies from fault to fault considerably, but it can be really important to map out the distribution of different types of breccia that we see in faults, meaning the different grain sizes of breccia in our breccia series of rocks within an individual fault zone. So though there's no orientation of class, like the class don't have an imbrication to them, or an elongation or stretching direction or metamorphic foliation necessarily, fault zones often have what we call an architecture to them, meaning there's often a fault zone core, like in this picture, the gray area, which is our fault gouge, and then the kind of less gray areas, the fractured protolith, and outside of that is unfractured protolith. So within the core of the fault, there are breccias of varying class size, but often there's gouge formed within shear bands of the fault zone. Okay, so it has this fabric to it that is parallel to the fault offset, more or less. And then we often have boundary zones outside of here, outside of the fault zone core, that are damage zones. So damage zones, they lack fault rock, but they're instead intensely fractured. And so not just from a structural geology perspective does it provide insight into how faults work, but the architecture of a fault zone can be actually in the brittle or in the breccia class of faults, so at shallower depths, they can be really important for providing insight into how to model the flow of fluids and groundwater and hydrothermal fluids, and understand the plumbing system of fault zones, and which is again also important in hydrocarbon exploration. Oops. Simply put, faults are they can be a conduit or a barrier for fluid flow. So here is a nice classic schematic picture of what that means. Okay, if fluid is trying to move this direction, okay, the core of the fault zone often has gouge in it, and gouge is basically a clay-like impermeable layer. And so fluids flow can be blocked, at least laterally. But these damage zones are highly fractured zones, and they're highly permeable, and they're often good conduits for the ascent of fluids. Okay, so cataclasites, again, recall they're composed of angular fragments, just like breccias, but they differ from breccias in a couple of really important ways. So here's 3 pictures of a cataclasite, just at different scales. You can see this is at a scale of outcrop or hand sample. Here's a quarter up here. And then this is a thin section zoomed out pretty far, 200 microns, and this is zoomed in pretty far, or it could be an SEM image. Okay, so they're significantly, in cataclasites, they're significantly more matrix material, greater than 50%. And you can see that in this picture here. Lots of matrix material between grains, and even in this thin section here, this darker colored stuff is matrix. So that matrix surrounds our brecciated class, and you can see the brecciated class pretty well at all scales in these pictures. And cataclasites are stronger and much more cohesive. And as I mentioned, they have this fractal character, again, meaning that at all scales, so from hand sample here to thin section to zoomed even in further, they all have this brecciated and fragmented texture with about 50% matrix and matrix support versus class support, like in our breccia classes of fault rocks. And again, the slip on these, just like in our breccia class of rocks, is accommodated by discrete fractures, discrete frictional sliding on grains, fracturing, and actually rigid body rotation oftentimes too. And so even though in a cataclastic zone, material appears to flow, it's actually accommodating motion by all of those frictional or all those brittle deformation mechanisms. Okay, and they also differ from breccias in that they lack a fault zone architecture fabric like the Breccia series of fault zone rocks have. So they don't have a central core gouge zone separated by a larger brecciated zone and a damage zone. And you can kind of see that we don't really have a central core zone in here, and nice kind of layered fabric in the fault material itself. And again, cataclasites, they form at much higher confining pressures and higher temperatures, so at depths from 4 to 10 kilometers here. And in fact, the cohesive induratic nature of cataclasites actually reflects comminution, which means the breaking down of our pieces into smaller and smaller brecciated pieces. It reflects comminution under somewhat elevated pressure and temperature. In other words, the crushing at these depths, it also increases the total surface area of the materials in the rock, and it makes them much more susceptible to chemical reactions and cementation. So that the tiny particles of crushed material, they end up getting cemented by hydrothermal and metamorphic minerals, giving the fault rock its characteristic strong cohesion, and it's often stronger than the surrounding parent, an unfaulted rock. Okay, our last type of rock that we want to look at in detail is pseudotachylites. Okay, so these are melts along a fault surface that freeze to glass. Glass meaning there's no crystal structure. You can see that quite well in this thin section. Okay, it doesn't have a crystal structure. It's a melt glass. It cooled really fast. And again, pseudotachylites, they have these vein-like arrays that come off of them and sort of have this spider web-like appearance. Okay, so those are our fault rocks, especially in the brittle realm. And in part 2, we're just going to talk about fault classification, basically by sense of slip. So come back for part 2, which is part 2 of lecture 14.